So I'm going to go ahead and get started since it's 8:30. First of all, thank you to all of you for coming out to the first talk after the party, which lasted till 2 in the morning. And for some of you, maybe later. I do say I really appreciate it, and I appreciate that you came out to the conference. I hope you're having a really good time. If you saw the abstract from my talk, I have to make a confession. I have not yet figured out how to transfer packets through wormholes. I'm working on it, so I can't actually defeat physics yet, but it's in progress. So I just wanted to let you know that we're not actually going to be totally laughing in the face of physics. Physics still gets in the way with this pesky thing called the speed of light, which is what my talk is a little bit about, but not really. It's really about how can we distribute data to the edges when we're dealing with multi-data center environments. So a little about me. My name is Anthony Eden. I run DNSimple, which is a domain registrar and DNS provider. I have been coming to CodeMash for a number of years. I was here during the polar vortex, where hair was freezing out in the hot tub. For those of you who remember that, good times. I'm disappointed by your weather. There's no snow on the ground now. I mean, it's just shameful how warm it is here. But don't worry, that's coming today. So, most of the time, I, and probably most of you, develop in a particular way, which is we have one computer with maybe a couple CPUs at most in it, and we're developing software right in that single environment, okay? Yes, we might be building web services and having a client come from our local machine and hit that web service, but in our local development environments, most of us do not simulate anything beyond just a direct network connection, not even leaving the computer in most cases. Maybe when you push stuff out to your staging environment or something like that, your QA environment, you might have a server set up. In fact, most of our systems actually operate in this same kind of environment. The vast majority of software that I write, at least, and have written in my career, operates on one or maybe a few servers, usually in a single data center. Even if you're writing things and deploying them to AWS, for example, if you're standing up a single EC2 instance, that's still one container on one server in one data center generally, all right? So most of the time, we can get away with just ignoring the truths of networks. Maybe we have to understand them a little bit, but local area networks generally work pretty well. So we just ignore those pesky things like latency due to how packets move throughout the network. Except sometimes. So for example, if you're building a global network of name servers, as I do. So in this case, it's not, you just can't ignore the fact that this is going to be distributed in multiple data centers. It's just a fact of our system is built up currently of 5 data centers, 3 in the United States, 1 in Europe, and 1 in Asia. We're adding on Sydney this year, making our 6th data center. And these geographically distributed systems present some really unique and interesting problems that we have to consider. And that's really what I want to talk about today. I want to give you but first of all, I want to go through and give you some examples of the impact on latency as you're moving data throughout a network, throughout a larger network. And then I want to talk a little bit about some of the challenges and some of the benefits and drawbacks. And then I will also show you various bits of software or talk to you a little bit about some of the software that you can use that exists already to help you accomplish this. And then if we have time, I have some extra credit material near the end. We'll see what happens. So I'm going to take 1 second here and see if I can get... There we go. I need my presenter notes here because I'm going to be talking numbers, and I will forget them if I don't have them on my presenter notes. So let's talk a little bit about the impact of network latency. All right? So as I said, these systems are complicated to build generally. And the reason is specifically because network latency is a thing that exists that essentially impacts your customers even if you don't know it. And once you start moving your data to the edges, it will impact you directly in a much more obvious fashion. So let's do a little bit of math. And we'll also use, I'm going to show some output, some tools that you might be needing to use in order to sort of determine network latency. It includes ping, which is essentially a simple network tool that goes out and sends an ICMP packet to all the different routers along the way. I'll talk a little bit about that in a second. And traceroute, which essentially does a similar type thing. All right, so ping actually will only ping the endpoint. Traceroute will actually send an ICMP packet to each router along the way, or each node. So let's talk about Chicago to Sydney, since it's in my head now that we're actually setting up a Sydney environment. So the distance as the crow flies from Chicago to Sydney is just shy of 50 million meters, okay? So that's what I'm going to be talking. I'm going to talk in meters per second, because that's what we have for the speed of light. We could convert it to kilometers and things like that, but I'm going to talk in meters. So just shy of 15 million meters as the crow flies. This would be like direct line of sight if we had it. We don't. Generally, that's flying over the planet. That's what it's going to look like. So let's do a little bit of math. So we have this 14.8 million meters divided by the speed of light, which is close to 300 million meters per second, gives us 0.05 seconds or 50 milliseconds. So if you could actually shoot a packet, straight line of sight, over the air, so you were actually traveling essentially at the speed of light, then you could still only get a packet out from Chicago to Sydney in 50 milliseconds. All right? So think about it. You already have like a starting point that most of us who are building web services when we talk about the speed of our web service, we're like, our web service will respond in milliseconds, like 50 milliseconds. Wow, it's fast. Okay? So the truth is that's just your local response area, or from wherever you're testing from. Generally, it's going to get a lot slower the further away you get, simply because the speed of light gets in the way. Now, that's theoretically. That's if you had that line of sight, which you don't. So we start looking at the real world. And let's take a look. What I did is I ran some ping and some trace routes, just as samples, from our servers in Chicago that I have that are at Server Central data centers, to servers that were out in Sydney. I picked a couple different providers, but I think I'm going to show one on the slides. So first of all, SoftLayer has a service where they run different ping time tests and things like that. So you can sort of see generally what the performance is around the internet right now. And there's numerous providers that do this. I'm going to look just real quick. So I'm going to show you a ping time. All right, 64 bytes, which is the size of the ICMP packet that they send. All right, and that's the address I sent it to. And the time was 250 milliseconds. Okay, that's significantly higher. So we've added on 200 milliseconds of latency. And that's this particular network. I ran some tests on another network, so Telstra, I think it is. That I was getting ping times of 198 milliseconds. So there's variation as well. And that's normal, and I'll explain in a second. But so why are we dealing with 250 milliseconds of latency instead of 50 milliseconds? All right, you can't really see this. I did that on purpose, but this is the basic output of a traceroute. That traceroute tool is probably already available on all of your machines, unless you're running Windows, but even then it might be available in some form. All right, so let's take a look at specific hops. So what traceroute does, as I mentioned, is that along the way, for each one of these hops, it's essentially telling a packet how many hops it's allowed to take before it should try to return back. That's what's called a TT, time to live. A number of routers it should go out to before coming back. So it does 1, hits the first router. Does 2, hits the first, then back 3, so on. And traceroute actually works. Let's look at the hops that seem to have the biggest discrepancy. Well, here's the first one that comes out. We go from ping times of less than 2 milliseconds all the way up to the 40 to 50 millisecond range. And you can see, you could sort of deduce from the naming, all right, we're in Chicago, and now we're hopping to Seattle. All right, so we're adding on anywhere from 40 milliseconds of latency just to hop from there. But that was the entire amount of latency to get out to Sydney. So what's going on there? And the answer is that one, there's no guarantees that we have a network that, first of all, we definitely don't have one that's going at the speed of light, most likely. So what might we have? We might have fiber optics. The truth is that fiber optic networks, even though they are transferring light, are not actually transferring that at the speed of light. Because the way that they work is they refract the light throughout. So it's not a straight line of sight. It's actually bouncing along the way. All right? We also might not be running. We might have something else. Most likely, inside of this network, there's a good chance we actually are running fiber optic across the United States in this case. But it's possible that you're not. You could be using other mechanisms that aren't fiber optic. So let's assume for a second that we add on this latency. OK, so that's just from Chicago to Seattle. Moving on. The next bounce goes from Seattle to Tokyo. And now we add on another 100 milliseconds here. All right? This most likely is pretty close to a fiber optic cable. All right? So again, if you look at, there's some blog posts out there that talk about this, that actually did some measurements and said, well, what are we looking at? The efficiency rating that on these fiber optic cables, the manufacturers will say like 80% the speed of light. The truth is often less than that. You know, there's lots of reasons. Cables bend. You have all kinds of different things that might come up. But there's also something else that might be happening. Each one of those hops, and I'm also ignoring, so I've got these hops here, but there's other hops along the way, because you hit a router. And that router can actually get congestion at any point in time. So in other words, it's dealing with a constant, like the load is not constant, it's constantly changing, in fact, depending on the amount of traffic that's being shunted through this system. All right? And traffic is dynamically changing because of the use of routing protocols. Most systems are using BGP, so they announce that they are available for routing through and who they're peering with. And so you can get latency simply by packets getting backed up. Because, again, it has to go into this machine and go out. They're really fast, but it's still some amount of latency, and it can be directly impacted by the volume of traffic that's going through at any time. Those of you who were here a few years ago when I did my presentation about the anatomy of a DDoS, understand, or if you've ever thought about DDoS, is basically one of the best attack vectors is overwhelming volume that simply in any given data center. If you have a multiple source of data and a flood of data, so the answer for data centers is to basically black hole your IPs and say, we're not going to route that anymore, because they have to think of all their other customers. All right, so there is a legitimate case where we see basically volume going into routers, not that we're running directly, but that our providers run, where it can have an impact on latency. All right, so moving on. Finally, we get one last hop that I wanted to show here. So here we have Tokyo to Sydney. And now we're talking about 125 milliseconds of latency added on. There's a little dirty secret about how networks work in the world. The answer is not the same. So peering inside of the United States is actually pretty efficient. There are a number of large providers. They have peering agreements with other large providers. All right, pretty solid. When you get into Asia, and so Australia is a special case, but when you get into Asia, for example, you have lots of little providers. And so you're going to have to peer with lots of different providers. So your packets are bouncing around crazy to get where they go through a lot more routers. It's effectively a monopoly. So you have two providers, I think, and the prices are ridiculously high. So easy. But they're not really incentivized to make great systems because there's no competition. All right. So what we can see here is that there are a lot of pieces along the way, and you don't think about that necessarily when you're developing in your local environment, that if you're going to be dealing with these distributed environments, you have to deal with the latency that's going to vary depending on where your data is going to be sent. I would like to propose to you, consider how your customers feel when they're the your server is in Chicago, all right? One of the reasons why we moved to multi-data center. So network latency is real. It's impacting your customers. And frankly, all you can do is deal with it, okay? So that's what I'm going to talk about next. If you're designing for your customers in mind, and they're all around the world, then let's figure out some techniques that we can use to actually deal with this problem. I'm going to talk about moving data to the edge because that's what we do, and that's what you're probably actually doing it. If you're running a system that CDNs, your CDN is doing that for you. That's exactly what they're doing. You're pushing into one location. They're distributing usually your larger binary files and like that out to remote data centers around the world. So what are the benefits of moving to the edge? So when you push data out to the edge, first of all, again, talking about your customers, in customer-facing systems, they have significantly lower latency for those customers. So imagine that same route, but for your customer in Australia, they only have to hop to a server in Australia. Now we're back down to the 20, 30, 40 second millisecond latency, or better, depending on how many data centers you have in that particular area. All right? That's a significant advantage from 250 milliseconds of just network overhead all the way down from anywhere to 25 to 50 milliseconds. That's pretty darn good. All right? The other thing that's really good is if you design the system correctly, you can actually survive outages in particular data centers in a much more effective fashion. All right? Because essentially, your system, if it's going to be able to respond from these different areas, so that if one offline, you simply allow that to happen and route your customer's request to the next nearest data center. All right? And the beauty of that is that they're going to see somewhat higher latency, but they're still system. Right? That's actually a really good trade-off and an effective way to basically mitigate significant outages. Whereas if you're in a single data center, you have no alternative, right? All right, so that's the benefits. So what are some of the drawbacks? Well, when you're moving your data to the edge, effectively is a hard thing to do. And that's what I'm going to spend most of the rest of the time talking about, is that particular activity. The other thing is that when data is inconsistent, so in other words, when your first database or your first data store has your write, but if it's not actually synchronizing writes out to everything else, you have some time where that inconsistency can be extremely confusing. So for example, if you had a system where you had user creation and they did that at your main data center and you were using asynchronous replication, I'll come back in just a second what that is, which is to say basically eventual consistency, and then that user happens to get routed to the other system, there's not going to be a user account there yet. So it's going to be very confusing. So factor into the design of your distributed system. So how do we do it? How can we move from a single data center to a multiple data center environment? All right. The first thing I'd like you to think about is what is our starting state? Our starting state in a single environment is I have a data store. Data is written to that single data store and read. Now, even if you have a logical data center, you may as well just consider it's so replication that it's in the same environment. Database is pretty good now at doing local area network replication quite quickly. All right, so that's not like I wouldn't even say, well, once you have a single data set, distribute the data sets. You're going to deal with a different set. Your starting state is have data written single in data center. Ending state is all servers in all data centers can reliably respond to customer queries with the same data. All right, that's where you're aiming for. And so once you starting state and the ending state, it becomes a question of trade-offs and what trade-offs you're willing to make. In order to decide that, you kind of have to understand your requirements. All right? So for example, let me give you some of the questions that you might want to ask yourself if you are preparing to build one of these systems and you're trying to understand your requirements. Here's some of the things you might want to ask. So in the event of a failure, what does this system sacrifice? Consistency or availability? Okay. One of the bonus areas, if we have time, I'll go a little bit into cap theorem. All right. And what I want you to just understand a simple rule in a multi-data center environment, partitioning is a reality. That is a factor of the network. It is not a get to make. You cannot say that that you're going to always have partitioning. It's not a thing. Therefore, I'm going to choose both. All right. You can choose different levels of them, of availability and consistency. But partitioning is a attribute of networks. It will happen. And partitioning is essentially, let's just simply say, packet does not arrive, all right, for some reason. All right, so which are you going to sacrifice? Consistency or availability? Assuming that consistency, you're going to sacrifice consistency, which is aim for availability, all right? Both of these things are desirable, but we're going to have to make a choice. So what is the acceptable delay for data synchronization? So what are eventual so that it becomes consistent? All right, the next question you should be asking yourself is, what is the acceptable latency? What is the acceptable latency for your customers? How many data centers do you need to be into? Where are the majority of your customers? What is the acceptable latency for you communicating out to those systems? Is it milliseconds? Is it seconds? Don't know. What are your security requirements? So the minute that you move outside of your nice little confines of your single data center, and again, if you're dealing with Amazon, if you're dealing with EC2 instances, and you're in one data center, you can kind of guarantee security, or you pay for it, pay that. But you can't necessarily do that going to other data centers, all right? Think about how are you going to do that? What is acceptable security? I'll go in. It's something you need to consider as well. The other thing you have to consider is, do you have data size constraints, okay? So for example, what is the total amount of data that you're in RAM at any one data center? Does the size of data that you will be accessing exceed the amount of available RAM and thus necessitate mechanisms to actually store that data on disk in remote data centers? All right? And if you don't exceed that limit today, when do you exceed that limit? What are your growth? Because this has a direct impact in how you design that system. All right? So, a couple of implementation options. Now, just a brief note here. I work mostly in the sort of open source technology world. I generally choose open source technologies or SaaS companies to provide things rather than deploying commercial software. So I'm going to be talking mostly in that space. If you are developing it with Microsoft's databases or Oracle databases, in many cases they have some of the same functionality. The same rules apply. And so I just want to briefly state that because my options are going to be mostly open source software or services. All right, so the first option is relational databases. You can rely on your relational databases replication technology in many cases. It's come a long way in the last few years because the demand is significantly higher nowadays for good replication strategies. Both Postgres and MySQL source database replicate. Funny enough, they both have effectively the same replication strategies. There's two general replication strategies that are common in the relational database world, and so does typically Oracle and Microsoft. Like they're all doing basically a similar type of replication. You either have block replication or logical replication, all right? Block replication, you effectively have a stream that is your log. It's your log of queries. And then what you do is effectively chunk that and send that across the network to get replayed on the remote server. It's all behind the scenes. You generally don't have to tweak settings, but you have direct visibility into what's happening under the hood. It's going to be compressed binary representations. So Postgres, this was the first type of replication being used in Postgres. The other type of replication, which is the logical replication, is the first type of replication that was used in MySQL. Nowadays, MySQL does both, and Postgres does both. 10 just came out and introduced logical replication with partitioning of, like, basically logical replication, which allows you to say, I want to execute this on all remote systems to become consistent. All right. So the goal is, how do we bring that remote system to the same, a consistent data set that matches what our primary node looks like? And so you could, like, let's say you have a series of, as they're coming into your primary, they're attempting to keep those things consistent. Now, there's two ways to do this. You can have versus asynchronous replication. I mentioned that earlier. Synchronous replication means that your master is going to wait until he gets confirmation that all of the followers that are getting that data have actually completed. The attempt there is to get ACID transactions, attributes, all of the. It's also really hard to do right, because this is where that whole pesky network problem gets in the way. And when a packet just like drops off, okay, wait a minute, just Asia just dropped off the internet. All right, what's going to happen now? All right, but only for like half a millisecond, and it's back. Packet was gone. Response. So there are different strategies for handling this. Usually, the software that you use for your relational database is going to have something built in to attempt to fix itself when that happens. It's going to get a failed response, and then it's going to basically say, okay, I'm going to go back and continue. And then what the problem you have to deal with is it might look to you like you lost that packet because you didn't get a reply. But in fact, the other packet was happily delivered. You just never got a reply on it. So now you send the same thing twice. All right. And, well, that's a problem because now you have conflict, right? Execute maybe the same thing. Or they get out of order. All right. So you have a series of operations, and they B, but they're executed in the followers in BA. All right. Well, if happen conflict, and the same problem exists as well in asynchronous replication. The difference is in asynchronous replication, the primary is not going to wait for a response. All right. It's basically assuming that that's being dealt with. Generally, you need specialized software to be able to deal with the asynchronous. But again, a lot of this is handled by the underlying database. Going back real quick to the notion of logical replication, same deal again. These things have to be executed without waiting for response. Conflicts, bad things start to happen. You have to be able to deal with it. For example, in Postgres 10, in their logical replication, if logical replication, it's a stop the world situation. It will continue. All right. And so that means now you have to go in and fix that thing manually, either by bringing the database back up to deal with, oh, my database is not there anymore. So how do that get into, I need to now take that entire and allow and decent performance, not as good as it was before, but at least correct, consistent responses. All right, so relational databases are definitely an option, and I would there first. But the second option is to use key value stores. All right, this is the whole NoSQL thing, basically. NoSQL is a fancy name for trying to get against SQL, but really saying, all right, there are a lot of variations on this. All right, they start from things like your simple in-memory caches like memcache. All right, memcache is one that's been around for a long time. And memcache is simply like an in-memory key value store, and you can tweak it a little bit, control like the size put in it and how many keys you can have in it and things like that. It's very basic. All the way from that to much more complex, that and Redis. So memcache and Redis are good examples of sort of, again, simple. They both support replication as well, as do a lot of them will have built-in replication mechanisms. So other examples from the simple side going to the more complex are things like React and Cassandra. So these are key value stores where you're going to have nodes. They're designed mostly for and more specifically high availability in a large data and environment. So the amount of data that you have to have exceeds the amount of RAM that you have available. You can no longer keep your entire data set in memory on one particular node. So you have to distribute that out amongst multiple nodes. Well, since you're there, take advantage of having multiple copies of that same data on multiple nodes, which means if you have a minimum of 3, so typically 3 is required for a quorum, and if one of those fails, you still have a functioning system, availability system. I'm not a huge fan of high availability. I mean, I like it, but I don't really believe in it because inevitably everything's just going to fail at once. So I'm a much bigger fan of mean time to recovery, minimum mean time to recovery, and trying to keep that really low. But essentially these systems exist specifically to deal with big data that exceeds the amount of data. Now, good news for me is our data set is small enough that it all fits into memory. So I generally don't have to deal with that type of problem at this point in time. In addition, there's other projects as well. So there's a project called Apache Ignite, which is big cache. So you write into the cache. And all of these are effectively can be treated as they're called databases in many cases. They're key value stores. It's a lot of names for saying basically, I have something that I can put data into and get it in and out fast. And I can cache that data. I mean, databases generally do that, right? They pull data from disk and they cache it in memory. That's their job. There's also these things that you might, if you're researching this, cast, I think is what it is. Yeah, it's an in-memory data grid. So again, this is where you're dealing with large data sets and dealing with essentially distributing that data across all these large data sets and making it easy to do queries as if it was a single data store, even though in fact distributed across a lot of data stores. Fancy name for effectively the same thing. And again, you have the same thing. You have synchronous versus asynchronous replication. Same set of problems. Does the primary wait to get confirmation that everything succeeded, or does it let it happen and deal and it's up to the ends to deal with it? So the followers that are out there to deal with it. All right, so databases, good. Another option is to with message queues. All right. So this is something like a RabbitMQ, a Kafka, kind of a ZeroMQ even if you've heard of that, which is essentially like a message queue that's not really a message queue. It basically gives you message queue patterns built right on top of a low layer networking. The thing about queues, if you're going to use them directly, of your applications that are at the edge essentially become the caching mechanism, and they're responsible for pulling things off the queue. That's actually a reasonable strategy in some cases. All right, so I'm going to assume that most of you know how message queues work. You put a message on, and then you have some sort of pattern for how things get, like maybe publish, subscribe, fan out, things like this. So the idea is simply you build your application to understand the message queue. You pull messages off the queue. Generally, at this point, you're going to ask for a durable queue. You're going to ask for one-time. The typical thing that you're going to get from queues is you're going to get applications that are aware of how messages are passed around, as opposed to talking directly to a data store. Queue messages generally need to be kept small because essentially you're sending a lot of them. So if you're dealing with a queue message that is small and your actual data that needs to be pulled in is larger, then you're going to have to go queue, handle it, and then get that from the data directly. So you're still dealing with the latency of grabbing that data from whatever data store it is. But because it's asynchronous and you control back to your central data store, removing the need for you to have synchronized data stores in your multiple data centers. Again, it's trade-off, right? It depends on what you're comfortable operating. Are you more comfortable operating message queues or distributed databases? You know, you have to sort of figure out what works for you. You can also combine the two, all right? So message queues plus store, for example. So now you have some little system, some little small thing that is pulling off that queue and into some sort of cache. All right. This way, your applications are still just talking to the cache, so they're just doing basic queries about like actually pulling, getting data off the queue. That's up to some little tiny application that's doing it. Added complexity for some parts of your application, but potentially easier for application developers because you can reuse this notion of pulling things off the queue and sticking it in the data store across multiple applications, as opposed to having to build in message queue handling into each of your applications. All right, so why do you choose to do custom replication, which is essentially what you're doing if you build on top of message queues with or without caching mechanism? Other, if you're building on message queues, you have a cache. It just may be your application's in-memory implementation. All right, so what are the benefits of doing custom replication? Well, you have more control over failure handling, failure conditions. So remember I mentioned Postgres 10, it stopped the world if your replication fails in replication. I think, I don't know MySQL very well. They probably have more tools doing that at rest. You can still break it. So you have more control over it. So you can decide that it's not a stop the world situation. Let's say you lose a message. You might say, well, my system is it combines notifications through event queues with some sort of polling mechanism that just verifies the consistency of the data after a few minutes. That might be totally legitimate. Or after 24 hours. Customers data, maybe they're using a warehousing mechanism, for example, and with a delay of some amount of time. Or maybe they only do once a week reporting on these things. All right, so you can combine a simple messaging system with a mechanism that will actually poll on a regular basis, or you could just go straight to polling. So there's better understanding of how the system is built in this case as well. It's not a black box, right? You can understand the inner workings of your particular examples of some of the benefits. But why not? It's going to be more complex. Like, you're trading away your simplicity because you are taking responsibility. Again, your mileage may vary. You have to decide if you need the complexity and if you need that in your environment. The other thing is that generally you're on your own when things go wrong. If things don't work the way you expect to in your replication system, you have to figure out why. All right. Whereas when you're dealing with existing replication systems, other cases have often been dealt with either by software through documentation, or you can even ping user groups and figure out, like, hey, what is going on? This doesn't make any sense. All right. So what do we do at DNSimple? I'm going to tell you, we started off with MySQL. Back in the early days, we ran our name servers on virtual private VPSs, so virtual private servers, like really cheap. And we were using MySQL with logical replication. And it worked fine for a while. Now, what we did next is, I'm going to please don't do this unless you really need to. And in fact, our decision that we made was based on a need that was totally non-existent. And I will take full responsibility for that because I built it. The need was, we were thinking, well, what if somebody wants to run our name servers or similar name servers out on their networks? And therefore, they need to be outside our firewalls. Oh, we'll just use HTTP as the way for, like, we'll use basically web sockets with HTTP so that we can get past firewall. So now we have a homegrown system. And our homegrown system essentially is a fan-out type solution where we have a centralized database. We have applications that send out notifications asynchronously to different little applications that are running on the edge that then go and say, okay, I now need to tell all of the name servers that are sitting out in my data center that they got data, and then they in return ask back for the larger data. So they get a small message that says, hey, data change. They then ask and say, give me the entire zone, and they pull it into memory. And then we have a caching layer using memcache on each of those data centers so that once we get that particular zone in cache memory, in memcache, we don't have to keep going back to our central database. So this is kind of like, it's a homegrown system. And one of the reasons for this talk is it's one we've been talking about replacing quite a bit. So I'm sharing with you knowledge that I have that I gained while trying to research this, so that with the hopes that it will maybe save you some time down the road. All right, so for your consideration, if you're going to be building a system like this on your own, first of all, you need security considerations, all right? Transport security, firewalls, and access control. So how is your data going to be secured as it moves between those data centers? All right, are you going to use HTTPS or some TCP over TLS, so some sort of encrypted protocol? Are you going to use a VPN with IPsec? Are you going to take a lower layer of the network protocol? You can use both. You can use something else. You need to first factor that in. So again, transport security is going to be one of the things you're going to be looking at. The next thing is firewalls. Does any system out of your firewall network need access to this? Because most of the systems that we've talked about, if you deal with database replication, you use that to your customers outside the firewall. Your applications will. All right, so how do they get access to that? How do you deal with access control? How do you verify that only authenticated systems are actually going to access the data that you've distributed out to the edge? How do you deal with changes of your security credentials? All right, we need to be living in a world where we're rolling security credentials on a regular basis. Most of us are not yet there, but we need to think about that. Well, if you need to roll security credentials in a distributed environment, how are you with that? Right, you have to have a place that deal with making sure you don't lose complete access to your entire network as you roll these security credential changes. Operational considerations. You need to think about things like unified monitoring. All right, so now all of a sudden you have all these systems that are spread out. You need to have somebody actually see the internals of what's going on in those systems. So you need to have a global view. And the reason you need it is because your humans that are involved in this are going to be going on in these systems. Problems inevitably do occur. Just a bit of information. Datadog, I highly recommend them. Service. So that's one example of you could do. You can build your own if you really want to. I recommend you do not. There are other providers out there as well that will do this for you. And essentially what you're looking to do is build dashboards. Operated systems has seen these things where essentially it gives you the key pieces of information that would impact the availability of your system. The other thing now you have to think about is aggregated logging. You can no longer go a box and go like, hey, tail the log there. That doesn't work if you're dealing with a distributed 5, 6, 10, 12 data centers and multiple servers in each of those data centers. You need to have a way to aggregate that logging. It has to be searchable. So now you have to bring all that stuff together so that you can search through it, because the volume of logs you're going to be producing is going to grow with each system, and it's all going to be intermixed. And so you need mechanisms for filtering and searching. And the reason you need this is because when that monitoring dashboard goes, hey, something's wrong, all right, you need to have basically logging in place that's going to be able to help you troubleshoot that. Again, I'm going to give not really, well, I'll say recommendations because we use it. I'm happy with it. It's a good system for centralized logging. It can take lots of data sources, jam them together into a log that then you can query. They have command line tools so you can essentially tails on your logs and filter it through command line tools as well. Incident management. So again, stuff's going to happen. Things are going to break. You're going to have data. Behave. You need to have a way to have your team be notified of this. This is common good behavior if you're operating systems, but as application developers, often we don't think about this necessarily. You kind of have to build that in. This notion of monitoring, logging, and notification has to be a part of your thinking, much more so in a distributed system, because otherwise your customers are going to see that first. You're not even going to know it's going to happen, and they're going to be the ones that are going to tell you. And it's going to be hard to troubleshoot if you don't have the tools that I'm talking about. We use PagerDuty. You can use whatever you want, but we find that to be good. All right, one last thing I want to talk about here. So I want to talk about distributed tracing. All right. So this is actually something that has seen very quickly for two main reasons. I don't know if anybody's spoken about any of the microservices talk, but microservices are a key factor for pushing this, because now you have lots of little services, and if you have problems of any particular, you need to have those problems. So distributed tracing allows you to do this by essentially creating a distributed span across for any particular request or any particular transaction effectively. And it lets you then break that down into its constituent pieces. If you ever use a tool like New Relic or something like that, this is that, but in a way that's and lets you actually for your application above and beyond any default set of tracing mechanism you might use. So there's something that's not relatively recent, open tracing, which is essentially an open standard for defining these distributed spans. Before you go into building a system like this, I would highly look and see if you can find there are existing bits of software out there that will help you do this. There are also services. Again, we are testing this out with Datadog because they're starting to support open tracing directly. I highly recommend looking at it. Definitely do that before you build anything custom. See if you can build on top of one of these existing systems. It's really useful for identifying bottlenecks, and it's also really useful for identifying latency and where that latency exists if you're dealing with these types of systems. All right, so in conclusion, latency impacts customer experience. That's a given, all right? So your customers, if you have a single data center and you have customers in foreign countries or wherever they are around the globe where your customers are traveling, they're impacted by latency right now, all right? So you need to keep that in mind and start thinking if that is a large segment of your population, of your customer population, the people you're writing for, because we don't develop in a vacuum, we develop to solve problems, then please start considering latency as one of those problems we're dealing with right now. And it has a significant impact on their experience. Ideally, both writes and reads customers. So in other words, when they save something to your data store, it's fast. When they read something from your data store, it's fast. But that's an ideal world, so you're going to have to make some trade-offs. All right? There are multiple options. Don't assume that the only option is I have to replicate my database. All right? That is not the only option. And there's no one-size solution that fits all for a particular problem. You have to look at your problem, you have to then say, okay, which of these possible solutions? Focus on your requirements and your verification. All right? When you get into these types of distributed systems, you have to understand what you're going to build, and then you have to verify that what you built solves the problem in a way over time and grows with your system over time, which means you have to have the tools in place in order to see into your system. You can't expect like your web framework or your software environment to necessarily provide that for you because they're built around these notions of monoliths and like centralized systems. Now again, that is starting to change, but don't expect that it's going to be solved completely. Be prepared to instrument your code in a way where you can see that across a distributed network. And finally, implement the technology you know if it fits the requirements. Don't say, all right, I really want to implement this technology for dealing with distributed systems. Answer is, I understand I will be able to verify built a good solution. I'm going to build a solution with a technology that fits, ideally one that I understand now if it supports my needs, right? Because otherwise, you're basically going to spend a lot of time building something without having any idea if it's really going to work for you. Well, generally, that's how we work anyways, right? So that's all I have for this. How much time do I have left? Like 15 minutes, I think, total? Yeah? Are there any questions, first of all? Before you go, I want to say feedback is really appreciated. They want you to give feedback on Attendee Hub. At the simplest level, you can give me stars. If you want to be more complex, there's a little survey that you can answer a question. I love feedback, so please do that. And then finally, DNSimple.com is my company. We do domain management. I would really appreciate it if you all come and buy stuff from me. It makes me very happy. And so I'm going to go ahead and wrap it up now. I think we're good, right, in terms of time. Unfortunately, I didn't get a chance to talk to you about cap theorem and ACID in depth. You're so disappointed. The good news is there's a bunch of stuff you can go and read on the internet. Go out, take a look. There's been some great things written up on cap theorem, and there's papers about it. It's actually really fascinating, and the rabbit hole goes down a lot deeper than this. So thank you all for coming out today. Enjoy the rest of the conference, and have a good day.